Hello and welcome to this video. So this video is part of the class Introduction to Artificial Intelligence and Machine Learning for Engineers. And what we are going to talk about in this video is to review some good practices in when you apply machine learning to solve engineering problems. What are the best practice to follow and what are the traps to try to avoid? So in this video, what we are going to do is first we are going to use this video as a summary of all the different good practices that we have seen over the previous lectures and over the previous tutorials. So the first objective of this video is to offer a review of all the things that we have seen and put them all together to have a practical way to remember what are the good practice to follow. And we will also introduce a few additional concepts, a few additional best practice to follow. So there's three main things that we are going to see today. The first thing is to provide a general framework for a machine learning pipeline. So by that I mean if you apply machine learning to a real engineering problems, what are going to be the different steps that you should be following? So it doesn't mean that all projects will necessarily exactly follow those steps, but I would like to provide a general framework that can guide what are the different steps and in which order you should follow those different steps when approaching an engineering problems using machine learning. The second thing that I would like to do is to review for each of those steps what are the best practice to follow and what you should be doing and what you should be avoiding to do, what are the common mistakes. And the last thing that I would like to review is once you have trained a machine learning model, then you will want to see if it meets your expectation or not in terms of the accuracy and the performance of the model. And if it doesn't meet your expectation, which is most likely going to be the case at the first iteration, because most of the time you need a lot of iteration before you can converge towards a machine learning model that meets expectation. So if it doesn't meet expectation, what you should be able to do is first to figure out what is the issue, what is the bottleneck, what is limiting the accuracy of the model. So having some tools to figure out like what is the issue behind the lack of performance that you are seeing is an important topic that we need to talk about. And the second thing is once you have identified the issue, how to address it. What can you do in practice to improve your model? And based on the issue that you have identified, then the solution, like what you need to do to improve your model, will not be the same. So you need to understand what is the issue so that you can deploy the right solution to improve your model. So let's start by reviewing the different steps that you should be following when you develop a machine learning model. And so for this, what we are going to review is what is the typical machine learning pipeline. So what are the different stages that you should be following for your project involving machine learning? So the first thing is once you have identified the problem, the engineering problem that you are trying to solve, the very first thing that you will need to do when you want to address this problem using machine learning is going to be to collect data. So you will need to be collecting some data. Remember that if you solve a problem using machine learning, then it means that the machine learning model will just learn from existing data. And in this case, it means that the machine learning model doesn't know anything about the underlying physics or the underlying chemistry or the underlying engineering theory behind this problem. So the only thing that the model can do is to learn from existing data. So collecting data, having access to data is going to be an important step that is a prerequisite when you run a machine learning project. So collecting data can mean potentially different things, and it depends on the problem that you are trying to do. If you are trying to train a machine learning models in order to predict something, then you need to make some measurements. You need to first make some measurements of different materials or different phenomena that you measure, and you need to measure it several times in different conditions, and you need to measure this system that you're trying to predict, the behavior of this system that you're trying to predict. You need to measure the output that you're trying to predict in all the various conditions that you want your model to be able to learn. By that I mean that if you're trying to predict the behavior of concrete under different conditions, for example, under different conditions of temperature, under different conditions of loads, under different conditions of relative humidity, if you don't train your model based on data covering all those different scenarios, all those different ranges of conditions, then your model will not be able to guess. If you want, for example, to predict what will be the behavior of concrete at elevated temperature, to understand how a fire would potentially affect the integrity of concrete, if you never measured the property of concrete at elevated temperature, then there is no way that the machine learning model can predict properly what would happen to concrete at elevated temperature, because it has never seen example of data involving concrete subjected to high temperature. So machine learning models, they are pretty good at interpolating data. So that is to say, if you measure the properties of concrete at two different temperatures that are close to each other, then the machine learning model will be able to predict what happens in between those two temperatures. But typically it's pretty bad at extrapolating. It's good at interpolating, so to predict what will happen in between the examples that you provided to the model during its training, but it's pretty bad at extrapolating. That is to say, if you train your model based on certain condition, it's going to be pretty bad at extrapolating to new conditions, because it has never seen what would be the behavior of the system under those conditions. So if you want to have a model that can be versatile and that can predict the behavior of your system over a large range of different conditions, then you need to have enough data covering all those conditions. So it means that you need to collect data. You need to collect a lot of data. The more data you have, the better your model will be, since it's only learning by example. But more importantly, you need to collect data homogeneously throughout the entire range of conditions that you want your model to be able to predict. So you need to measure a lot of data, but you cannot have all the data for a given domain and having some other domains, for example, domains of temperature, for which you don't have data. You need a lot of data, but more importantly, you need to have data for every range of conditions for which you want to be able to make some prediction. If you think in terms of machine learning, it means that you have some features. Those are the inputs of your model. You have an output. If you want your model to be robust, then you need to collect some data for all the possible values of the features. For large value, for low values of each of the features, you need to cover some data that span homogeneously throughout the feature space. In every possible combination of those features, ideally you need to have some data. That way the model will not have to learn what happens for certain features. It will have data. It will have some previous example that it can learn from to predict what will be the influence of each of those features and what will be the effect of having a very large or very small value for each of those features. So that's going to be the first step. It's collecting data. So you need it can be performing some measurements if you are measuring something. It can be trying to access data that have been already published or data that are available somewhere. Or it can be gathering data from different sources and gathering them together within a single data set. If you cannot perform measurements, maybe you can perform simulations. So you can generate synthetic data using simulation. That's another way to generate data. Of course, if your simulation is wrong, then the machine learning model will be also wrong, since it only learns from the data it is exposed to. So you need to make sure the data that you provide to your model are good quality data. And you need to make sure the data are organized in terms of the input and the output. So the data needs to be labeled. So for example, it means that if your goal is to be able to recognize pictures and predict if there is a cat on the pictures, then maybe you already have a lot of pictures, but then you will need to put some effort into labeling those pictures. And by that I mean that you will need to have somebody looking at a lot of those pictures and manually saying, yes, there is a cat, or no, there is no cat. So for example, if your goal is to predict a machine learning model that can analyze a picture of a person and then predict if this person is happy, sad, surprised, angry, or other kind of emotions, then in order to learn this, it needs to learn from a lot of pictures, and it needs to be, those pictures needs to be labeled, which means that somebody has to review a lot of pictures and then select for each picture if this person on the picture is angry, sad, happy, surprised, or any other kind of emotions. So which means that sometimes collecting data might simply mean labeling data. So attributing a label to the data that you have. So this is going to be a key step within the machine learning pipelines, because if you don't have data, and if you don't have good data, or if you don't have enough data, then training the machine learning model is not going to be efficient, and most likely your machine learning model will not be reaching a very good performance if it doesn't have enough data to learn from. So the second step, after you have collected data, the second step will be to prepare data. So to do some data preparation. And this typically can take quite a bit of time, maybe even more time than training the machine learning model itself. So when I say preparing the data, it can mean several things, and we are going to come back to this, but it can mean cleaning the data. For example, if you collect some data, that data collection is most likely going to be made by humans, and humans can do mistake. They can type some typos when they enter data in the database. So they can make some error when they do the measurement, or some data might be missing if the human forgot to input certain data. So you can have various problems within your datasets. In real-world datasets, you always have a lot of potential issues with the data. So you will need to invest some time to do some cleansing. You will need to do some data cleansing. So the data cleansing can be trying to detect when there is a typo. For example, if the data was entered in the datasets, and if there is a figure missing, or if there is a period missing, or if there is an extra zero that has been added, or if there is a data that should be a number but is actually like a text character or something like it. Those are some obvious typo. They need to be fixed, to be corrected. There can be some outliers. So if there is if you test a concrete, and in one of the concrete is behaving very differently from the other concretes, then that's an outlier. It might mean that maybe there is something wrong with this concrete, or somebody added too much water in this concrete, or something else. Sometimes we know what went wrong, sometimes we don't know, but in any case, this measurement is an outlier, and most likely, if it's an obvious outlier, then it needs to be removed, or the experiments needs to be repeated to try to remove outliers. Outliers maybe will not be a big problem if you have a lot of data, because then the outliers is just going to be 1 point, like which have a very small weight as compared to all the other data. But if you don't have so much data, if you just have a few hundreds or a few thousands of data, then having outliers is going to be a big issue, because the outliers will make your model learn from wrong data. So the model will start to predict behavior that are not real, behavior that are based on the outliers rather than being based on the real data. So identifying the outliers and removing them or replacing them by good data is something that can potentially be very important. So for this, you have a certain number of outlier detection algorithm that can be used. For example, a very simple one is to do a clustering analysis, just like we saw in the previous lecture. And if you find that there is one cluster that contains only one data, then you mean that this data point is very far away from the other data points. And in that case, it's possible that this single data point that belongs to a different cluster then might possibly be an outlier. You can, since supposedly as an engineer you also have some intuition or some understanding about the problem that you are trying to solve, sometimes you know already, you have some experience about what should be some reasonable values for the feature. So you can also use your experience to determine whether a point is an outlier or not based on what is expected and what is reasonable or not. For example, if you measure the density of a given material, and if you find that you find a negative value for the density, then that's obviously wrong. That's not possible. So in this case, that's a point that needs to be removed. Otherwise, it would affect the model, and the model will start to think that it's possible to have some materials with a negative density. So that's why it's important to remove outliers. Another example of data preparation might be to remove duplicates, for example. So if you have several times the same data, that might not be necessary. So you would just remove data that are just equivalent to each other. The problem with duplicates is that if you have several times the same data, then the model will attribute more weight to these data points. So it's usually a good idea to remove duplicates to avoid having a bias where the model thinks that this data point is more important than the other, because it is just duplicated several times. So it will contribute more to when you calculate the RMSE of the model or the MSE of the model. If you repeat the same data point several times, it will contribute more to increasing the error of the model. Okay, and another important thing is the feature engineering. So creating the right features, deciding what are the right feature to include in the model, and what are the features that maybe should be removed. This is very important. So engineering features, creating new features, or just simply feature selection, like selecting what you think are the most influential features for your model, is a very important step. If you don't have the right feature, if you don't choose the right features, then you won't be able to predict the output. If you want to predict the price of a house, and you don't know, if you don't choose the right features, if you don't know the size of the house, if you don't know the number of bedroom, if you don't know the age of the house, then you won't be able to predict its price. Like, your model might be very good. If you don't have access to the right features, the most influential features, then there is no hope that you can build a model that can predict the price of the house if you don't know the size of the house. So you need to select the right features. On the other hand, it's dangerous to add some features that are not useful. So you need to make sure you only add the right features, and you remove the features that are not useful, the features that are not influential. So once you have collected the data, once you have prepared the data, cleaning the data, choosing the right features, the next step will be to choose the model. You will need to choose the machine learning model that you are going to use. So this will be the step of the choice of the model. So in this case, so you need to ask yourself, so step by step, is it First, is it a case of supervised or unsupervised machine learning? So step one, that's typically a pretty obvious answer depending on whether you have a label or not. Is it a case of regression or classification? Again, this should be pretty easy depending on the possible values of the output. If the output is a discrete value or a continuous value. In some cases, it's not necessarily a black and white answer. Like in some cases, you have a model that you can either treat as a classification model or as a regression model. For example, like if you want to predict the magnitude of an earthquake, you can say, I want to predict the magnitude. I want to predict a continuous number that can be 3, 3.1, 3.2, etc. Or you can say, I just want to group earthquake into low intensity earthquake, medium intensity earthquake, or high intensity earthquake. So that would be now a classification problem. Or you can say, I'm going to group that into magnitude 1, magnitude 2, magnitude 3, magnitude 4, and I will not bother to predict whether it's actually 4, 4.1, or 4.2. I just want to classify them in terms of their magnitude as integer number. So if you want to do this and predict the magnitude in terms of 1, 2, 3, 4, or 5, or 6, then that would become a classification model. If you want to predict the exact value of the magnitude as a 3.4, a 3.5, 3.6, etc., then that becomes a regression problem. So it depends on the way you want to approach the problem. And then once you have identified whether it's regression, classification, clustering, etc., then you need to pick the algorithm that you want to use. So we have seen different things. We have seen polynomial regression, linear regression, logistic regression, artificial neural network, or k-means for the clustering techniques. Of course, there is much more model that are available, many more models available, many more algorithms, a different approach, etc. So it's impossible to cover everything in this class. So you need to think about, based on what you know, based on what you have experience with, and based on what you think will be the best model to approach the problem that you're trying to tackle, then you can try to think about, okay, what is the best algorithm that I should use to solve this problem? So this mostly comes with experience. There is no unique rules on what is the best algorithm, but at least based on your experience, you can think about, do I expect that I should choose a linear or non-linear model? Should I choose a model that can be described by an equation, or is it better that I use a model like an artificial neural network that is more flexible and it's not going to give me a clear equation, but it can fit a pretty complex relationship between input and output. It also depends on how many features you have. What's the number of dimension of your system? If you have just one or two features versus if you have a lot of features. If you have a low number of features, maybe polynomial regression might be a good choice. But if you have like hundreds or thousands of features, then maybe artificial neural network might be a better choice. So depending on all those factors, and based on your intuition, based on your experience, you will need to choose the right model to approach the problem that you are trying to tackle. Then, so once you have chosen the model, then the next step will be to train this model. So it's going to be the stage of the training. So you are going to expose your model to the data in the training set, and you are going to make the model learn. So this is the stage of the learning. So this is when the model is learning from the data that you collected, from the data that it is exposed to in the training set. So remember that learning is not something magical. It's just that you have some weights in your model, whether those are the weights of the coefficients of the polynomial regression model, or those are the weights that are connecting the neurons in your artificial neural network. and the model will try to adjust those weights in order to be able to map the inputs to the outputs, to be able to predict some outputs that match with the outputs that are within the training set. And the way you achieve this is typically by the steepest descent, the gradient descent algorithm, where you calculate a cost function. So you need to be able to have a cost function that tells you how good or how bad your model is. You need to calculate the error of your model, and then you need to calculate the derivative of the error of your model with respect to the weights. And then you need to try to find the weight that gives you a minimum error. So you calculate the derivative of the error with respect to the weights, and then you try to change the weight to go in the direction of the negative gradients. So you calculate the gradient, and then you want to minimize the error. So you go in the direction of the negative gradient to try to minimize, to change the weight so as to minimize the error. And ideally, you want the error to become the minimum. So you want at the end the gradient of the error with respect to the weights to become close to zero, which means that you have reached a minimum. So in certain cases, you need to repeat this training several times, especially when you have some methods, some machine learning method that depend on some initial values for the weights. It's possible that in some cases it might get stuck into a local minimum for the error function. So it's always a good idea, when you can afford it, to repeat the training several times, just to make sure you have reached a good satisfactory global minimum for the error of your model, and that your model didn't get stuck into a local minima for the error, for the cost function. So that's the step of the training. Step 5, this is the step where you will need to tune the hyperparameter. So you will need to do some tuning of the hyperparameter of your model. So the hyperparameters of your model, each machine learning model is using a certain number of parameters. In the case of polynomial regression, it can be the maximum polynomial degree that you are allowing. In the case of artificial neural network, it can be the number of neurons. It can be the type of the activation function. It can be the number of hidden layers. So you have various parameters that you can change, and depending on those parameters, your model will behave differently, or your model can be more complex or more simple. So you need to be able to change and to tune the hyperparameters, the parameters that describe the architecture of the model. So remember that there is two types of parameter in a machine learning model. You have the parameters themselves. Those are the weights. This is what is changed during the learning. So during the learning, you adjust the model parameters, like the weights of the models. Now, at the stage of the hyperparameter tuning, you are not changing the weights, you are changing the hyperparameter. Those are some parameters of the model itself, describing the architecture of the model, or it can be the learning rate that you are using into the gradient descent algorithm, or it can be other parameters about the polynomial degree, or etc. So those are now the hyperparameters. So those are the model that describe the complexity of the model, how complex or how simple the model is, or the architecture of the model, etc. So those are different from the weights or the bias of the model. So the parameters of the model that you adjust in step 4, this is the parameters that will dictate the relationship between input and output, and the hyperparameter that you change in step 5, this is what dictates how complex the model is, or how does it learn from the data. So once you have adjusted the hyperparameter, the step 6 will be to evaluate the model. So you need to evaluate how good the model is. So this is, of course, an important step because it dictates whether you are successful or not in implementing this model. So this is when you will test how good the model is. For this, it's important that you know what you expect. Like, what is your criterion about a successful or unsuccessful model? How good your model needs to be. So, and then based on this, you can decide, okay, is my model having a performance that is good enough or not? And if not, then you need to be able to understand what is the bottleneck of your model, what is limiting the accuracy or the performance of your model, and decide how what needs to be changed in order to fix this. So there is different things that can be changed. Maybe you need to collect more data. Maybe you need to better prepare the data. Maybe your feature engineering was not done right. Maybe you didn't clean properly the data. Maybe you didn't choose the right model. Maybe the hyperparameters are not correctly tuned. So there can be many things that can go wrong when you train a machine learning model. So when you evaluate the model, you need to understand, like, if something went wrong, you need to have some way to understand what went wrong so that you can focus your effort into doing the things that are actually going to be useful, that are going to increase the accuracy of the model. For example, if you realize that your model is not right, and if the model is not right because it doesn't have the right hyperparameter, the hyperparameters have not been tuned properly, if you just say, okay, my model is not right, I just need more data, then you will invest a lot of time and money to get more data, but that's actually not going to help because it's not the data that is the problem in this case. It would be the hyperparameters that are not properly trained. So in order to focus your efforts or your resources into doing the things that are actually going to be useful for the model to improve the accuracy of the model, then you need to have some kind of diagnostic tool to understand what is the key limitation of your model. And if you understand what is the bottleneck, what is the problem, then you can try to solve it or to invest your efforts into doing the steps that are needed in order to address the limitation of the model, collecting more data or having new features, etc. So that's the step of the evaluation of the model. Once you have reached a model that is satisfactory, then the last step is going to be to use the model to make some predictions. Usually when you train a machine learning model, the point of this exercise is not just to train the machine learning for fun, it's to have a model that can be used to make some prediction, a model that can be used to replace humans, maybe that can make some choices instead of having humans make those choices. So once your model has been trained, then you can use this model to make some prediction or take some decisions or make some judgment or do some actions that would typically be done by humans. So this is the step where you actually deploy the model and you use it in practice for what you wanted to use this model for, to solve the engineering problems that you wanted to solve. So now let's review a few good practice. Most of them we have seen those good practice already either during the lecture or during the tutorials, but it's good to summarize them all, to have them all together, to keep all those good practice in mind. So the first thing is regarding the data preparation. So the step that comes just after collecting the data. So when you prepare the data, there is a few different things that you should make sure you do or avoid doing. A common mistake is to forget to randomize the data. So you need to make sure you shuffle the data, you randomize them. By that I mean that when you collect data, typically you will tend to collect data in a certain order. By that I mean that if you are going to measure the properties of a given material at different temperature, then you will tend to measure at a low temperature and then increase gradually the temperature. So when you train your machine learning model and when you are going to split the training data into training set, validation set, and test set, then it's important that you had first shuffle the data, that you have randomized the data. Otherwise, what you don't want to do is to have all the low temperature data being used as a training set and have all the high temperature data being used as test set. So unless it's specifically what you want to do, if you want to test how well your model can extrapolate, for example, unless it's specifically what you want to do, then you need to make sure you randomize the data so that your model can learn at the same time what happens at low temperature and at high temperature. It can have some example of data that are representative of all the possible conditions it can be exposed to in the future when you make some prediction. So randomizing the data, shuffling randomly the data is an important step that can avoid training some models that are biased and that cannot generalize well to other conditions. Another common thing that can cause some issue is to forget to normalize the features. So it's not always needed, but in many cases, you will have certain features that have very different range of values as compared to other features. Some features are always very small. Some other features are always very large. Some features can change a lot. Some features will not change that much. For example, if you're trying to predict the price of a house, the number of bedrooms in this house, it can just be 0, 1, 2, 3, 4, and that's it. But if you're trying to predict the size of the house in square meter, it can be 20, 30, 100, 1000. Like the range of possible values for the surface of the house is going to be a larger number. It's going to be a number that can change a lot. So if you don't normalize the feature, if you don't do some feature normalization, then your model will put a larger weight on the features that change a lot, and will think that the features that don't change so much is actually less important. But this doesn't. It's not because a feature changes a lot, or that a feature is larger than another one that it's more important. Because it also depends on the unit. Like for example, if you decided to express the surface of the house in square kilometer, then the surface in square kilometer would always be a very, very small number. So the value of the features depends on the unit that you choose, which is not a good thing. So it's always a good idea to normalize the features so that all the features have the same weight, and you don't have a feature that varies more than another, or you don't have a feature that has a higher value than another. So you can normalize the features either by standardization or by a min-max transformation. So we have talked about those different methods in previous lectures. So like the exact method that you are using doesn't matter so much, but it's good to normalize the features to make sure that there's not going to be a feature that becomes more important than the other. Normalizing the feature is also going to make the training of the model faster and more efficient, because you don't have a deformed feature space that is much more elongated in one direction as compared to the other. So it's going to make the training of the model faster. Another problem that is more specifically to a classification problem is to make sure you have a balanced data set. By that, I mean that if your goal is to predict the value of a given class for the output, you need to make sure you have enough training example for all the values of the class. It would be an issue if you have certain classes that have much more training examples than other classes. For example, if you're trying to predict, again, you have some pictures of persons, and you want to predict if they are happy, sad, angry, or surprised. If you have 10,000 pictures of people that are happy and only one or two people who are sad, then your machine learning model will necessarily think that everybody is happy and will not manage to learn what are the characteristics of a person that is actually sad. Because if the model is always predicting that the person is happy, it's going to be right 99% of the times, because 99% of the picture that is provided to the model are about happy people. So it will not bother about the sad people, because there's just so few examples of sad people that it can just predict that everybody is happy, and the error that the model would be making would be very small. So to avoid this, you need to make sure that you have as many happy people as you have sad people in the datasets. It doesn't need to be exactly 50-50%, but you need to make sure it's a comparable size. Like there is not a significant difference between the number of happy people and sad people. And if you just don't have that many examples of sad people, then you can either try to create more examples by finding more pictures of sad people to add to your training set, or maybe in this case it might actually be a good idea just to remove some of the pictures of happy people, to reduce the fraction of sad people, to avoid providing too many examples to the model that are happy people. You want to make sure that the example that you provide remains balanced, so that the model becomes aware that people are not always happy, that they can be sad or happy, and that there is it needs to learn that those two states of emotions are possible for people. And the last advice that's very important for data preparation, and that can also inform for all of those different problems that we just discussed about, is you need to, as much as possible, visualize the data. So whenever possible, you need to plot data. And that's something that is very important, because by plotting the data, you can realize a lot of things. You can realize if there is an obvious outliers, if there is a point that is very far away from the other data. That's something that's going to become very apparent if you visualize, if you plot the data. If you have a distribution that is good, it's like if you have most of the data being very small, but just a very few small numbers of data that are very high, then maybe if you don't plot the data, you will not realize this. And maybe if you realize that you have a lot of small data and just a few very high data, then maybe it's going to be a good idea to transform this feature and taking its log. Because if you have only a few very high values for the data, those very high values are going to be dominating the model. They will be contributing the most when you calculate the error. So that's going to mean that all the small values, the data points with the small values for this data, will have a pretty low weight and will not matter that much. So just think about this. For example, if you have some data like this, so you have different values of y and x, you have quite a few data points at low x and at low y, and then you have just a few examples at very large y. So if you do this, those data at very large x or very large y, they will have a very, very important, very large importance in the training of the model. Because if you do a slight variation of the slope of your model, so let's assume that you have a first model that is doing this, or you slightly change the slope and now your model is doing that, or you slightly decrease the slope and your model is doing this, then most of those data points, they will just create a very small error. But if you take those data points here, like the error that those points are going to induce is going to be very high. Like those points will create like very large values for the error of the model. So the error of those points will be much larger than the error of all those points combined. So those points here will not matter. So for this, it's good if you take if you do a log transformation, for example, so that you can make sure that when you take a log transformation, then very large value will not look so large anymore. So it's going to put a more equal weight on all the values, all the data points, to avoid that certain data points becomes much more important than others. And this is only possible to do when you visualize the data. If you don't visualize them, if you just look at them in your Excel file, then there's no way you can realize those things. So visualizing the data is going to be very important to see if you need to do some feature engineering to transform some of the features. If there is an obvious outliers, it's also going to give you some intuition about which model you should use. Is it a linear model? Is it a nonlinear model? It's going to tell you if some of the features appear to be redundant with each other. Some features might be very correlated. Which feature is the most correlated with the output? If you're doing a clustering analysis, it can tell you how many clusters should be expected. So the more you can visualize the data, the more you can get this intuition that is going to be very useful to understand if there is something wrong, or it's going to give you some guidelines on what you should be using, what kind of model you should be using. So the more you can visualize the input, the output, the relationship, the distribution of the features, the distribution of the output, all those things, the number of data in the different classes, etc. Like the more you can visualize this within plots, then the more you can make some informed decisions on the different things that you can do in this data preparation step. So the second thing that I would like to talk about is regarding the choice of the machine learning model. So for this, when it comes to choosing a given algorithm at the expense of another, this relies a lot on what you know and what you don't know. It relies a lot on your experience, on your intuition. So it's not possible to really have some general advice or to say that we should always be using this method or the other. There is not a given method that is superior to the other. There's just the right method for the right problem. So there's not going to be a method that is always going to be superior to another method. It's not like artificial neural network is always going to be better than linear regression. Sometimes linear regression can actually be better. So you need to choose the right method for the right problem. And this comes with intuition. It comes with previous experience. So that's important to practice a lot in order to get this intuition. That being said, in general, a couple of advice that you should be following is that in general, it's always good to start, but also to favor the most simple model. If you have two models that gives you the same performance, but with different level of complexity, it's always better to choose the most simple model. You should be favoring simplicity, because a model that is more simple than another, even if those two models have the same accuracy, a more simple model is more likely to be right. If you have two different explanations for something, the most simple explanation is usually the most likely to be actually right. When you have a very complex model versus a very simple model, the simple model, assuming it has the same accuracy as the complex model, is more likely to be more robust. A more simple model can never be so wrong. It might not necessarily be always accurate, but at least it will not do crazy, unexpected things. A very complex model can sometimes do like very crazy thing. It can look like it's working pretty well, but it can become completely unrealistic in other conditions because it's very complex. It has a lot of degrees of freedom. It can vary a lot. It can have a high variance. So a more simple model is always going to be a better choice, assuming that you have two models that have the same accuracy. You should choose the most simple model. Of course, if you have a complex complex model that works well, that have a very high accuracy, and a simple model that doesn't work well, then it means that in this case the simple model is too simple and cannot reproduce the complex relationship between the input and the output. So you should not always be using a simple model if it just doesn't appear to work well. But if you have two models that work equally well, then choosing a simpler model is usually going to be a better choice. It's going to be a more robust description of the relationship of the input and the output. The second thing is to favor, whenever possible, the interpretable model. So to favor interpretability. By interpretability, I mean, how can you understand what the model is actually doing? And by that I mean that if you train a linear model, then you understand very well what the model is doing. It's creating, there is a slope that tells you about the increment. If the feature increase, how much will the output increase? And there is an intercept which tells you what's the value of the output when the feature is 0. So you understand very well how this model is working. If you have an artificial neural network, then there is no way you can understand how the network is transforming the input into the output. It's going to give you an answer, but you don't know why. And that's a problem, because sometimes if the model is doing something wrong, then you have no way to understand why it is predicting this wrong value, because it's like a black box. It's a very complex relationship between input and output. So it's not possible to understand why the model is predicting this thing. The other thing is that in many cases, in engineering or in science, it's good to have a model that works, but it's also good to understand how and why the model is predicting something. So if you are training an artificial neural network, then it's very unlikely you can learn anything. It's very unlikely you can learn any new knowledge from this model. You will not learn any new physics. You will not learn any new chemistry, because it's just going to give you an answer, but you don't understand why. If you train, on the other hand, a linear or maybe a polynomial model, then you can get more understanding about why the model is working, or what is exactly the nature of the relationship between input and output. And maybe you will be able to gain some new physical knowledge, some new chemical knowledge by having a model that you can understand, having a more interpretable model. So typically all the linear or polynomial model, those are models that can be described easily by an equation that is relating the input to the output. So that's an interpretable model. Logistic regression is also pretty interpretable, because you can also have access to the relationship. It gives you the probability of belonging to the different classes, and you can access this information by looking at the weights of the coefficients. But when you have an artificial neural network, then it's very hard to understand what the model is doing. In theory, you could look at the value of the weight. The artificial neural network is also an equation. It's just a very, very large equation that relates the input to the output. So the problem is not that it's not an equation. It is also an equation, but it's a very complex, nonlinear relationship that with a lot of weights, a lot of parameters, a lot of bias. And when you have something so complex, even though it is just based on mathematical operation one after the other, it is still something that you can express as an equation, although a very large equation. It's so complex that you cannot understand what this equation means. And if the model is not predicting something realistic, then it's very hard to understand why. So in many cases, you will have to use artificial neural network or other complex techniques of this kind, just because a simpler model will just simply not work. But again, when you have the choice between, for example, a polynomial model or an artificial neural network, and if they give you the same performance, the same accuracy, then it's usually a good choice to favor a more interpretable model, because you will be able to learn more about this model. You will be able to understand why the model is predicting what it is predicting. And that's going to be a more reliable model because it's not going to be a black box. You can see what is occurring within the model. So it's always a good idea to favor simplicity, but also to favor interpretability. So then the next step that we're going to summarize is the training of the model. So once you have chosen the model that you want to use, once you have collected the right data, everything, so you will need to train your model. And for this, so this is something we have discussed several times, but it's very important to be able to train your model based on a fraction of the data, and to keep hidden to the model some fraction of the data that you are going to use at the very end to test how well the model is doing. If you use all your data to train the model, then you have no way to know how well the model is actually doing when predicting some new unknown data. So it's always very important to keep a fraction of the data until the very end, to hold on those data, to keep them invisible, fully hidden to the model, and to only use them at the very end to test how well the model is doing. So typically what you will be doing is starting with your training set. So this is your training set. This is all the data that you have accumulated. So you will want to keep a certain fraction of the data, for example, something about 30% that you will want to use as a test set. So the rest will be the training set. So the training set is what you will use to train your model, and the test set is what you will keep until the very end to see whether the model is accurate or not. So that's going to be the first thing. And for this, again, it's important that first you shuffle the data so that there is no ordering of the data. You want the training set and the test set to homogeneously sample the data set. So you don't want to have more small or more large data into the training set. It needs to be randomly split within the training and the test set. The second thing is that training the model requires to tune some hyperparameters, and this is going to be accomplished again by keeping another fraction of the data unknown during its training and using this data to test how well the model is generalizing and what is the best value for the hyperparameters. So for this is that the second thing that you will be doing is within your training set, you will need again to split this training set into a given fraction that you will use to train the model. So let's say, for example, something about 80% will be used to actually train the model, and the remaining 20% will be used as the validation set, which will be used to tune the values of the hyperparameters, to choose what's the best number of neurons, to choose what is the optimal polynomial degree, etc. So this is important to have this second range, this second collection of data that is used to set the right values for the hyperparameters. So sometimes what people do is that they just use one test set, and they use this test set for the validation and also for testing the data. So sometimes people do that, especially when they have a very small data sets, but it's typically not a good practice, because if you use this test set at the same time to decide what is the best value for the hyperparameter and also to test how accurate the model is, then you end up with a model that can be potentially biased because you tuned the hyperparameter specifically to reproduce the values in the test set. For example, in the case of an artificial network, you specifically chose to tune the number of neurons to reproduce this test set very well. So maybe the number of neurons was specifically chosen for this test set, which means that this test set now is not a fair test for the model to see how well it's predicting unknown data. Maybe now it means that if you provide some new unknown data for the model, maybe it's not going to be predicting them very well because you chose specifically the number of neurons to optimize it to reproduce this test set, and maybe it's not going to work well for another test set. So it means that it's important to separate the data that you use to tune the hyperparameter, that's the validation set, and the data that you use to test how well the model is doing to predict unknown data, that's the test set. So it's important to have both a validation set and a test set. So that being said, for the validation set, typically what we use is the cross-validation techniques, where rather than using a single validation set and a single training set, you are going to use the k-fold cross-validation. For example, in this case, that would be a 5-fold cross-validation, where you are going to repeat this 5 times, where each of those 5 times you are going to train the model based on 4 of the folds, and you are going to validate this model based on the remaining fold, and you are going to repeat this k times, or repeat this 5 times in this case, and then at the end you will get an average value for the validation, the error of the validation set, and you will also be able to have a standard deviation to see how stable or how much variation there is when you train your model based on those 5 training sets, and whenever you validate it based on the 5 validation sets. So you will get an average score for the validation set, an average RMSE for the validation set, but also you will get a standard deviation. And those 2 information can help you to tune the hyperparameters. So this is the step where you will tune the hyperparameter of your models, so as to your goal when you tune the hyperparameters is to minimize the validation set error and to minimize the standard deviation of the validation set error as well. You want to minimize the average error that you are making when predicting the validation set, but you also want this error to be pretty stable. You don't want to have a model that sometimes will predict a high error for the validation set, sometimes a low error for the validation set. So you will tune the hyperparameters to minimize the error and also minimize the standard deviation of the error. So once you have done this k-fold cross-validation, then you will have chosen the optimal hyperparameter for the model. At this point, it is good to just retrain the model based on the entire training set. Like once you have identified the best values for the hyperparameters, now you have identified what is the polynomial degree, what is the number of neurons, then you can retrain it based on the entire training set. So this training set plus the validation set. At this point, what you don't want to do is just to pick the model that was the best within each of those 5 repetition of the 5-fold cross-validation, because this model might not necessarily be the most representative, or you don't want to take the average of all those models. In this case, it's just good. Like the role of the validation set was just to tune the hyperparameters. Once those parameters have been tuned, then you can just retrain the model based on the entire training set. You don't need to reuse each of those validation sets. The point of the validation set is only to set the value of the hyperparameters. So once those hyperparameters have been set, then you can just retrain based on this 70% of the entire data set. And then once you have done this, so you will retrain your model. At this point, when you retrain the model, so the hyperparameters are fixed, you decided them. So you decided how many neurons you have, how many layers, but the parameters of the model, the weights, the bias, etc., those things can potentially change once you retrain the model. And once you have retrained the model based on the entire tested training set, then you will now test it. So those 30% of the data that I use in the test set, they are kept hidden until the very last moment. And now at the very last step, once you have identified the best hyperparameters, you use this remaining 30% to test the accuracy of the model. And now it's a very fair test for the model, because those data are fully hidden. Like, the model has never seen those data. It has never seen those data to optimize, to tune the value of the hyperparameter. So it's a very fair test of how well the model will behave in real life. How well is it going to be able to predict data for new data that it has never seen before, for new values of the features. How well is it going to be able to predict the value of the label? So you need to keep this test set fully unknown until the very end, and you need to make sure there is enough data in this test set to be a fair test of the model. So at this point, when you test your model, it's important to be able to be in position to say, okay, my model is good enough. I can just stop here. Or my model is not good enough. It needs to be improved. It's not as accurate as I would like to be. And for this, it's important that you have some intuition and some ideas of what is the desired accuracy that you want. So for this, there's two things that are important. First, you need to be able to understand what the accuracy means. Like, if you think about the accuracy of the model in terms of an MSE, a mean square error, that's something that is very hard to interpret. Like a squared error is something that is very hard to get some intuition about what it means. We know that a high MSE is bad, a low MSE is good, but how low does it need to be? That's something that is very difficult. If you want to predict the price of a house in dollars, the RMSE will be the average of the square difference between the predicted price and the real price. That's the unit of the RMSE will be in square dollars, which is something very hard to understand what it means. So you need to have an accuracy that is possible to understand. So for example, if instead of using the MSE, you use the RMSE, the relative mean square, the root mean square error is going to give you an error in dollars. It's going to tell you on average how much is your error. Is it are you making an error of $1,000, $10,000, $100,000? So now you start to have a number that makes sense. But sometimes this number is also not easy to understand. What is more easy to understand sometimes is to do a percentage error. So for example, you can calculate the mean average percentage error or the relative root mean square error. Then that's going to give you a percentage of how accurate your model is. Is it accurate plus minus 5%, plus minus 10%, plus minus 20%? So when you have a model and you have the accuracy of this model in percentage, then that becomes much easier to understand if the model is accurate or not. So that's the first step. If you want to know what is the desired accuracy for your model, you need to express this accuracy in a way that makes sense, that humans can understand. The second thing is you need to have an idea of what is the expected accuracy of the model. And this depends a lot on what you're trying to predict. If you are trying to predict a value that has a lot of fluctuation, like for example, if you're trying to predict the strength of a given concrete, the strength of a given concrete can depend on a lot of things. And even if you measure the same concrete several times, you will not find the same strength because there is some inaccuracy in the strength measurement. There is something intrinsically random in how at which stress the concrete will break. Different concrete, there is a lot of variability in the concrete and the way it develops strength over time. So you should not be able, you cannot expect to predict the strength of a concrete with an accuracy of plus minus 1 psi or plus minus 1 pascal. That's not possible, because it would be a lower accuracy than the intrinsic variation of the data themselves. So you need to be aware of what is the uncertainty of your measurement. When you measure something, whenever you measure this thing, if there is an accuracy of plus minus 5%, just when you do the measurement, then your model cannot become better than the intrinsic uncertainty of the experimental data themselves. So in order to decide what is an acceptable and a non-acceptable accuracy, you need to be able to understand what is the variability of the data, what is reasonable to be able to predict, and what is not reasonable. You need to be aware of what is the intrinsic variability of the data. You need to be able to have an idea of, if you want to use this model in practice, what kind of accuracy do I need to make this model useful in practice. Some certain cases are fundamentally random. For example, if you're trying to predict the price of a given stock, then it's something that is pretty random. So maybe you don't care whether the model is super accurate or not. You just want to predict whether the stock is going to increase its price or decrease its price. So maybe even if the model is not very accurate, maybe that's still acceptable. And you know that your model can never be super accurate and predict the price of the stock to with an accuracy of just a few cents, just because it's just impossible. Like this, the stock price is too random, so there is no single model that could possibly predict the stock price with an accuracy of a few cents. So for this, you need to be able to understand what the accuracy mean, and you need to have an idea of what is an acceptable accuracy. What is the accuracy? What is the lowest possible accuracy that you can possibly get, because it's the intrinsic level of variability or the level of confidence that you expect about the data that you have measured. On the other hand, if your goal is to predict if a picture contains a cat or not, then the accuracy ideally it should be very close to 100%, because it's either it's a cat, either it's not a cat, and there's nothing random about this. And there's just a very, very maybe less than 1% of the case where even human would disagree whether it's a cat or a dog or something else. But in 99% of the cases, a human would be able to know if it's a cat or not a cat. So your machine learning model, the level of expected accuracy should be as close as possible to what a human would be able to do. So in this case, if you have a model that can predict with a 70% accuracy if a picture contains a cat or not, maybe in this case this is not going to be acceptable, because it's too far from what a human could do. So it's important to know what is your level of expectation, what is the expected performance, the expected accuracy that you want for the model, and it depends on what you would like your model to do, to be able to do. Is it useful to, if it's useful to predict with a 70% accuracy if there is a cat or not, then why not? But in this case, it's pretty far from what a human can do. So that would be probably a pretty bad choice to use a machine learning model rather than a human for this task. But if you want to predict something that has more intrinsic variability, something that is more random, or something for which you don't have all the information available, you are missing some of the features, then you need to be aware of what is the best that your model can do. Because if you have some measurement and this measurement is accurate with just an accuracy of plus minus 10%, then your model can never be better than this, and you can invest as much money as you want, as many data as you want. Your model will never be able to become better than this 10% accuracy. So the next step is, if the machine learning model is not as accurate as your expected accuracy, if it doesn't perform as well as your objective, as what you want to achieve, then you need to find a way to improve the model. So the question in this case is, what can you do? What are the different options that you have to improve a machine learning model? So there is different things that you can do, and different solution of things that can be done to improve a machine learning model. But the first thing is to see what are the different options, but more importantly, you will need to pick the right options. And depending on what's the issue, what is the bottleneck, what is limiting the accuracy of your model, then maybe rushing towards one of those solutions might not be the best choice. You need to be able to understand what is going on with the model, what is limiting the accuracy of the model, so that you can pick one of the different mitigation, one of the different solutions. So the different things that can go wrong within a machine learning model is that first, maybe there's not enough data in the training set. So in this case, the solution, if there is not enough data, the solution would be to get more data. So that is to say, to increase the size of the training set. So in certain cases, that's possible to do this. It's just going to cost you some money to train more data, because you need to pay people who will do some measurement, or to pay people that are going to label data, or you need to invest your own time to gather data, or you need to find more data to source or to mine more data. In certain cases, it's just like you cannot get more data. So that's in that case, that would not be an option. You have to do with what you have. Getting more data is just simply not possible. But in any case, the lack of data is a common problem in the machine learning model. So in this case, the solution is can be simple or very complex depending on the nature of the data. But in this case, the solution would be just to get more data, to increase the size of the training set. And in many cases, that will help, but not always. So that's not the only thing that can possibly go wrong. Sometimes you have more data than needed, and still your model is not performing well. One of the other things that can potentially go wrong is if your model is too complex. So you have an overfitted model. Then in this case, the solution to this would be to simplify the model. That is to say, for example, you can use some regularization. So you can use the lasso algorithm, for example. You can remove some features. You can decrease the number of neurons. So you can force your model to become more simple. So this is what the problem that you face if you have an overfitted model. So if you have overfitting, then the solution to this is to make the model more simple. Then the next step is the opposite. If your model is actually too simple, then in this case the solution is also pretty simple. You will want to make the model more complex. So that's the other way around. Now you will need to add new features, increase the polynomial degree, increase the number of neurons, etc. So in this case, this is what you need to do if you have a case of underfitting. So if the model is just too simple, it's too biased, you need to make the model more complex. The fourth possible thing is that maybe you just didn't choose the right method. Maybe you need to choose another method depending on the data that you have, depending on the nature of the relationship between data input and output. Then a given model might work better than another one. Sometimes you have a very linear relationship between input and output, then you should choose linear regression. Sometimes you have a very nonlinear relationship. Sometimes you have a lot of features. Sometimes you have few features. So different algorithm will work better in certain situations, and some other algorithm will work best in other situations. So one possible solution, if the algorithm that you are using is not the right one, you will need to switch to another algorithm. So you will need to try another regression method, another classification method, etc. You will need to switch to a new method and see if that helps. And the last thing that can possibly go wrong is that maybe you have the right model, it's just properly optimized, it's not underfitted, it's not overfitted. You are using the right model, you have enough data, but maybe you are missing some features. So by missing some features, I mean that you have enough data, but you don't have the right features, you don't have the right input. You're trying to predict the strength of a concrete, but you don't know how much water this concrete contain. If you don't know how much water there is inside the concrete, you can know everything else about this concrete. You can know the type of cement, the types of aggregates, how much cement, how much aggregates. If you don't know how much water there is in this concrete, there is no way you can predict the strength of this concrete. If you don't know the surface of the house, it's impossible that you can predict its price. So having the right features is something that is critical in order to be able to predict it. If you don't know the cause, then you cannot predict the consequence. So it's possible, you need to think like, do I have all the information I need? And if the answer is no, then it means that the solution to this will be to add new features, new influential features. You might be missing some features, and adding them is going to increase the accuracy of the model. So those are the different things, the different options that you have when it comes to improving a machine learning model. So the question here is, once you have a machine learning model, and if it's not having the level of accuracy that you want, that you are expecting based on your understanding of what kind of accuracy should be acceptable or should be desired, then the question is, how do you know what is the problem? And how do you know which solution you should be following? In which of those 5 options should you invest your time, your effort, your money, or whatever? You need to choose, like, where should you place your effort in order to improve your model. And for this, you need to understand what is going wrong with the model. So you need some kind of diagnostic tool that can allow you to understand what is the key bottleneck, what is limiting the accuracy of the model, what is the key thing that is missing in the model. So one very important diagnostic tool to understand what can possibly go wrong with a given model that is not giving you the expected accuracy, the accuracy that you would like this model to have, is to understand how the model is learning as it is exposed to more and more data. And this is something that you can access by constructing the learning curve. So the learning curve is not something we have talked about so far, but it's something that is very important in practice to understand when a model is not working as expected, to understand what is the issue. So plotting the learning curve, and we are going to see what is this learning curve and how to get it. Plotting the learning curve is going to give you a lot of very useful information to understand if the model is not working well, like what is the key bottleneck, what is the issue with this model. So the idea of the learning curve is going to be to train the model based on the training set and see what it is predicted based on the validation set. But rather than training the model based on the entire training set, so if you take your data sets and, for example, divide it into a 70% training and the rest would be a validation set, let's say 30% validation in this case, rather than training the model based on the entire training set, what you will do is to see how the model is learning as you provide more and more data, as you expose the model to more and more data. So what you will do in practice is that rather than training the model based on the entire training set, what you will do is just take a small portion of this training set and train the model only based on this subset of the training set, where you will just pick randomly a given fraction, maybe 5% of the training set. Then you will repeat this by now taking a little bit more data. Maybe now you will take 10% of the training set and you will train this model based on 10% of the training set. Then you will repeat again, you will train it based on 15%. Then you will train it based on 20%, etc. So you will gradually increase the number of the data points that you are using until at the end you have used all the training set. So usually if you just want to train the model and get the best accuracy, then you will use the entire training set. But here we want to see how the model is learning as you gradually increase the number of data points in the training set. So you are going to manually increase the size of the training set. So you still keep the same validation set. So the validation set remains constant and it remains the same. The size of the validation set remains the same, but you will just manually increase the size of the training set gradually. And what you will be plotting is a plot, so that is called the learning curve. And this plot is going to be, you will be plotting the error function. So we typically write this error j. So you will calculate either the MSE or the RMSE, and you will calculate the error for the training set and the error of also the validation set. You will plot those two information, and you will plot this as a function of the size of the training set, the size of the training set that you are using. So depending on if you train the model based on 10, 15, 20%, etc., you will calculate for those different sizes of the training set until you use the entire training set. At the end, that's where your plot will stop. You will plot what is the error that your model is making when predicting the training set itself, and what is the model that your model is making when predicting the validation set. So let's try to think about what this learning curve should necessarily look like. So at the beginning, when you have very few training example, when you start with a very low training set, so just a few points within the training set. So just to make a schematic of this, so let's assume that I'm going to show here a plot with the label as a function of the feature, and in this case, just for the sake of illustration, I'm going to put only one feature, so just one feature, and you want to predict the corresponding label. And let's assume that at the beginning you have very few training examples. So just to make it clear, let's assume that at the beginning you have only 2 training examples, and then you have your validation set that looks like this. Those are some values that you are trying to predict for your validation. Then, so initially, when you train this model, so you will train the model based on the red crosses. So initially, when you have very few data points, then you will always be able to train a model that can go perfectly through those points. Like if you have only 2 points, for example, you can just have a straight line. It's going to perfectly go through those 2 data points, which means that initially when you're training your training set is very small, necessarily the error that you are making for the training set is going to be very close to zero, because it's very easy to train a model that goes exactly through each of the points perfectly. So the error would be zero or very close to zero. On the other hand, the error that you are making for the validation set is going to be pretty high, because your model is just has been trained based on a very small number of training examples, so it's going to be pretty bad. It doesn't understand well enough what is the relationship between input and output, so your model will not generalize well. So the error for the validation set will be pretty high. So this is what you will start like. Any model will start like this, with a very small error for the training set and a very large error for the validation set. This is always going to be the case. Then as you start to increase the number of points in the training set, so this is when you have a small training set, so this is what you get for a small training set. Then when you have a larger training set, so now you increase the size of the training set. So the validation set has not changed, so you still have those two blue points here, but now in addition of having only the two training example, now you start to have more training example like this. So now that you have this, so your model will be able to learn better the relationship between input and output. So now you will get something like this, a better model. So once it is exposed to more data, the first thing that is going to happen is that now you have much more data points into the training set, and each of the data into the training set can have a small variability, which is due to the uncertainty of the measurements. So now it's going to be impossible to find a model that can perfectly go through each of the points of the training set, and that's probably would not be a good thing anyway. So now you will start to have an error when interpolating the training set. Your model will not be able to go through every single point of the training set, which means that when you start to increase the size of the training set, now the error that you are making for the training set will start to increase. When you look now at the validation set, so you will also be making a small error, but now your model has learned from more data points, so it has been able to learn better the relationship between input and output, so it's going to be able to better predict the value of the validation set. So the error for the validation set will decrease and will become lower and lower as the model becomes better at predicting the value of the output as a function of the input. So the validation error is going to decrease. So this is going to be the general trend of the learning curve. So this is the learning curve here. You plot the value of the validation error and the training error as a function of the size of the training set. The validation error will always decrease with the size of the training set, and the training error is always going to increase. Okay, so you will always, the size of the extent of the training error is always actually going to increase when you increase the size of the training set. So this is going to be the general shape of the learning curve. It's always going to look like this. That being said, different models will have slightly different shape for the learning curve, and based on this you can understand what is the key limiting thing of the key bottleneck of the model. So this is what we are going to talk about now, is to understand now if you take a given model, you calculate its learning curve. Based on this, how can you understand, how can you read the learning curve as a diagnostic of what is going wrong within the model. So the good thing about the learning curve is that it can help you understand if your model is underfitted, or if your model is overfitted, or if you are missing data, if you need more data. So for this, you need to understand what is the typical signature of an underfitted model or an overfitted model in its learning curve. You need to see what is the typical learning curve of an underfitted model versus an overfitted model, or a model that has not just been exposed to enough data. And if you are able to know what is the typical signature of those kind of issues, then by looking at the learning curve, then you can decide what does the learning curve suggest? What kind of problem is the learning curve suggesting? So for this, let's first look at the case of an underfitted model. So a model that is too simple, what would its learning curve look like? So let's start to see if you have a simple model. So let's plot, again, let's start with showing what an underfitted model would look like if you train the model based on the small training set first, and then what would happen if now you increase the size so you have a larger training set. So in both cases, I'm going to plot the input and the output. So the output as a function of the input. In both cases, I'm going to put the training example. So let's start with the validation set. So you have the same validation set all the time. So those are the data that you are trying to predict, to see how well your model is generalizing. And to be able to learn this, the model will be exposed to some data within the training set. So initially, your training set is just going to be very small. You only expose a small fraction of the training set to the model, and then you just expose more data to your model. So if let's see what the model would be doing in this case. So again, as just like we saw on the previous slide, if you have a very small number of data points in the training set, even an underfitted model, even a very simple linear model, will always be able to predict the training set perfectly. If you have very few points within the training set, you can always find a model that will go exactly through those points with an error of 0 or a very small error. So now let's plot the corresponding learning curve. So the learning curve is the x-axis is the size of the training set. So that's the x-axis, that's what is changing. And on the y-axis, we are plotting the error of the validation set and the error of the training set. So in this case, so for the training set, so for very small training sets, the error j of your model will necessarily be very small, because initially you can find a model that is going to perfectly go through every single point of your training set, but you will have a very high error for the validation sets. So initially it will look like this. Then if we look at the case of a large training set, so remember that it's an underfitted model. So your underfitted model is going to be too simple. If the model is too simple, then it's going to look like something like this. if you fit those data by, for example, a straight line, which would be an example of an overfitted model, what you will see is that the error for the training set is still going to remain pretty high. So you will, in this case, now you will have a high error for the training set. You started with a very low error, but now the error for the training set is going to be pretty large. So this is what you will get now for a large training set. You will make a large error for the training set because the model will not be complex enough to interpolate the training set. It's not going to be able to go through the points of the training set because it's just too simple. It's not complex enough to represent the complex relationship between input and output. So now your curve for the error of the training set will look like something like this. Initially, when you have very few points in your model, despite the fact that it's underfitted, it can still go through every point of your training set, so the error is pretty small. But very quickly, the error will increase because your model is just not complex enough to go through the point of your training set. Now, if we look at the validation set, then your model is still going to be bad. If your model is bad for the training set, then it cannot be good for the validation set. The validation set is always going to be at least as good or at least as bad, but it cannot be better than the training set itself. So when you expose the model to more data points, it's still going to be a little bit better, but it's still there's no chance you can predict the validation set very well because it cannot even predict the training set. It cannot even predict the data it is trained on. It's just not complex enough. So the error for the validation set is going to decrease, but it's going to remain pretty high. So it's going to look like this. So in this case, in blue, that's the validation set error, and in red, that's the training error, the error of the training set. So now what are the typical signature? If you see a learning curve that looks like this, how do you know that it's an underfitted model? What are the typical signature? So the first thing that you need to know to decide if it's an underfitted model or not, you need to know what is the desired performance for your model. You need to know what is the error that you would like, ideally, your model to do. So let's assume in this case, your model, you want your model to be able to predict the output with a given accuracy. But in this case, since your model is not complex enough, the error of the model is going to be higher than the expected performance. This is the desired performance that you would like your model to have. So the first thing that you can say for an underfitted model is because it's too simple, the error for the training set, but also the error for the validation set, it's going to be significantly higher than the desired performance. But this, maybe you didn't need the learning rate to get this. Like even if you look simply at the final performance of the model, then you could have seen that the error for the validation set and the error for the training set is higher than the error that you were expecting. So the learning curve is not going to be so useful for this, but that's nevertheless a first signature of an underfitted model. The error for both the validation set and the training set is higher than the desired performance, the error that you would like your model to have. So that's the first thing. The second thing is that in the case of an underfitted model, the validation error is going to be very close to the training error. Because in this case, your model is just so simple that it cannot predict the training set. It cannot even predict well the training set. So in this case, its ability to predict the training set will be as bad as its ability to predict the validation set. So typically, what you will see in the case of an underfitted model, you will have a very low difference between the validation set error and the training set error. Like they will converge towards the same value. That's a sign that it's an underfitted model. And the last signature of an underfitted model is that it learns very fast. And by that, I mean that very quickly the error is converging, and the error then doesn't change. So it learns fast. And it means that when you increase the size of the training set, it doesn't learn more. Like the error doesn't change. The model just remains stuck and doesn't change anymore. Why? Because it's a very simple model, so there's nothing else to learn. There's no way to change. It has learned everything it could. And in that case, exposing the model to more data is actually not helping, because it's just not complex enough. There is nothing to change. No more degrees of freedom to be changed. So those are the three signatures of an underfitted model. The error for the training set and the validation set are close to each other. That's the first thing. Those errors are much higher than the desired performance. So it's a high error. That's the second thing. And the model is learning fast. So it's converging. The error is going to be converging very fast, and the error of the training set and the error of the validation set is not changing so much as the training set is increasing, because there is nothing else that the model can learn. So it doesn't benefit from having new data. So if you see those three features, those three components, those three signatures, then it's very likely that it's an underfitted model. So in this case, it's seeing this information can help you understand what's the right solution, because it means that in this case, for example, increasing the size of the training set would not be useful. If you just increase the size of the training set, it's not going to help. Your model is just going to, the error is just going to remain stable like this. This is what you would get if you increase the size of the training set. That would not help at all, because that's not what the bottleneck is. That's not the prime with your model. So in this case, increasing the number of data points would just have no effect at all. What you would need to do in this case is to prevent your model from being underfitted, which means that either you are missing some of the features, you need to create some additional features, or you need to make the model more complex. You need to increase the polynomial degree. You need to go to a more complex model, like maybe an artificial neural network, so that you have a model that is more complex, that can better interpolate the relationship between the input and the output. So that's going to be the solution in this case. If you have an underfitted model, then you need to make the model more complex, adding more features, more dimensions, or more complex, or less linear model that is not going to be limited by having just a linear shape, that can be more complex to be able to fit better the relationship between the input and the output. So now let's see what would be the signature of now an overfitted model. How can you figure out that your model is overfitted? But just by looking at its learning curve. So again, let's plot some example where now we put so y as a function of x, so the observation y, the label y as a function of the feature x. So we are going to have always the same validation set. So the validation set does not change. Its size and the data points remain the same. And again, so you will now provide first initially a small training set and then a large training set. So initially you start with only let's say something like this, with 2 points in the training set, and then you start to predict to add more points in the training set. So now we take the example of an overfitted model, so a model that is too complex than it needs to be. So let's see what the model would be doing in this case. So when you start with a very small training set, again, your model will necessarily be able to go through every single point of the training set. So in this case, because the model is overfitted, it's going to be very complex, and maybe your model will look like this. It will go through every point of the training set, and it will have a complex shape like this. So let's see in this case what would be the learning curve. So again, I'm plotting the error J both for the training set in red and for the validation set in blue, and I'm going to plot this as a function of the size of the training set. So initially this doesn't change. It's always true in the learning curve. Like initially, when you have very few data points that you use to train, the model will be able to go through every of those single data points. So the error will be very low. This doesn't change between an underfitted or an overfitted model. So the error will be almost zero in this case. However, in this case, like because the model it just hasn't learned enough, like the error for the validation set is going to be very high. So this again is still the same as with an underfitted model. There is no difference. Like the training set is just too small in this case. The main difference now is going to be what happens when you have now a large training set. So in this case, the model will be able to be complex enough so that it's not going to remain a straight line, because it has more flexibility to be more nonlinear, to be more complex, to have a more complex relationship on how to map the feature to the output. But because it's overfitted, your model will look probably like something like this. So it will go through every point, it will be very deformed like this, and it will be too complex than it needs to be, so as to interpolate as much as possible the training set. And in this case, what you're doing is that here you are fitting the noise of the training set, which means that your model is overfitting. It's not capturing the trend of the data. It's just being deformed too much to fit the training set too well, and it just fit the noise of the training set and will not generalize very well. So now remember that your model, like the best model that you would like, would be in this case probably something like this. So if you compare the expected error, so if this is here the expected error that you want, so this is the expected the desired performance for your model. Now if you look at what is the error that you are making for your training set, the expected error that you are expecting for your training set would be something like this. Like you would be expecting, just because there is some flexibility, some variability in your data, you would be expecting a certain error. But actually what you find is that when you look at the difference between your data and your black model, actually the error of your model is actually much smaller than your desired error. So now the error, because your model is so complex, because it's so deformed, and because it's making a lot of effort to go through every single point of your training set, now the error of your training set will remain pretty low and will remain lower than what you think should be the desired performance. So the error for the training set is still going to increase, because it becomes harder and harder for the model to go through each point of the training set, but it's going to increase slowly like this, and the error of the model will remain lower than the desired performance. So in this case, it looks like your model is actually doing better than it should, because it's deformed so much. It's going through every single data points of the training set, so it's actually having a lower error than it should. Now let's look at what happens for the validation set. So when you look at what should be the error between the validation set and your model, so you should expect a pretty reasonable error like this, but actually, because your model is so deformed, it is making a very large error. Like the error in predicting the validation set is very large. It's because now your model is overfitted. It doesn't generalize very well. It has too much variance. So now the error of the validation set is still going to decrease, because your model still is able to learn by having more and more data, by being exposed to more and more data. But the error of the validation set will remain pretty high, because your model is just too complex, too overfitted. So in this case, the learning curve will look like something like this. The error for the validation set will slowly decrease as you increase the size of the training set. So now let's see and summarize what are the typical signature of an overfitted model. So the first thing is that if you compare the error for the validation set and the error for the training set, and if you compare it to the desired performance that you would like to have, then you would find that the error for the training set is actually smaller than the desired performance. So the model is doing better than it should for the data of the training set, but more importantly, it's doing not as well as it should. Like the error for the validation set is higher than your desired performance. So your model is doing a low error, a very low error when predicting the data, when interpolating the data of the training set, but it's doing a large error when predicting unknown data from the validation set. So that's the first signature. The second signature is that in this case, you will have a big difference between the validation set and the training set. When you have a model that shows a large difference between the training error and the validation error, that's a sign that it's an overfitted model. So in this case, the validation error will be significantly higher than the training error. So that's the second signature. So this is going to be a large difference here. The last signature of an overfitted model is that it's very slow to learn. It takes a lot of data points to learn. In this case, the way you can see that is that first, it takes a lot of data for the error to converge, or like the error does not seem to converge, like the error seems to continue to decrease, like the error does not converge just yet. It still continues to decrease slowly with the size of the training set. So that's another signature of an overfitted model. The error, the validation, the learning curve is very, very slowly decreasing. So in this case, those are the three signatures of an overfitted model. Now, if you have an overfitted model like this, and if you realize that, so there is a large difference between your validation error and your training error, and your model is very slow to learn, so now it can help you figure out like what is going wrong in your model. So in this case, there is two possible solutions. So your model is overfitted. So solution number one is that you may want to make your model more simple. So to add a regularization term, to use lasso to penalize having too many features. You may want to remove some of the features. You may want to decrease the number of neurons. You may want to decrease the polynomial degree to try to make the model less overfitted. So that's one thing. The other thing that you can do is just to add more data. When you have an overfitted model, you can usually overcome the overfitted model just by adding more data. And the way you can see this is that if you look at the learning curve, like you can see that if you were able to add more data, it would slowly converge towards the desired performance, because in this case your model is just very complex. So if you provide more data, so the model has a lot of weights. If you don't provide enough data, the model cannot figure out what's the right value for all those weights, and that's why now your model starts to be too deformed, like to adjust all the weights to go perfectly through every point. And in this case, it's the weight are adjusted so as to fit the noise of the data rather than the trend itself. But if you provide much more data, then at some point the model will not be able to fit the noise of the data anymore. So your model will adjust its weight to just fit the trend of the data. So adding more data can always solve a problem of an overfitted model. It's just gonna take probably a lot of data to be able to properly fix the value of all the weights. So there is two things that can be done here. Either actually your model is just intrinsically too complex. There's just too many weights. So you can remove some of the features, some of the neurons, reduce the degree. So you reduce the number of weights that needs to be optimized. And then you see what the model is doing. If the model now becomes underfitted, then it means that actually reducing the complexity of the model is not gonna be enough. It means that it's you cannot afford to have a more simple model. It's not gonna give you the level of desired performance. In this case, option 2 is to get more data. If you have actually a complex relationship between input and output, then you need a complex model. And if you have a complex model, then you need a lot of data to train this complex model. A complex model will contain a lot of weights. In order to fix the right value for all those weights, you need a lot of data. So in this case, using the learning curve and by extrapolating the learning curve, you can estimate how much more data would you need in order to have a validation error that would converge towards the desired performance. And you can estimate based on this how much more data is needed. Do I need to increase the data by 10%, 50%? Do I need to double the number of data? Do I need to multiply the number of data by a factor 10? So plotting the learning curve can help you figure out, is having more data, is it going to help or not? If it's an underfitted model, having more data is not going to help. But if it's an overfitted model, and if the model is has to be complex, then having more data is going to help, and having more data is necessary. That's something you can figure out with the learning curve. And by looking at the learning curve, you can estimate how much more data is actually needed, how much more data would be needed in order to have the right level of performance. So finally, let's finish by seeing what would be the learning curve of a good machine learning model, so an optimal machine learning model. So in this case, what you would expect is that the learning curve will look like this. So the learning curve will still be about plotting the error for the training set and the validation set as a function of the size of the training set. So this doesn't change. The beginning still doesn't change. For a very small training set, your model will be very good for the training set and will be very bad for the validation set. Then you have here your desired performance. Okay, and if you have a good model, then the learning curve will look like this. As you increase the size of the training set, the error for the training set is going to increase and will saturate, will plateau towards the desired performance. Remember that the error for your training set, you don't necessarily want the error for the training set to be as low as possible, because it cannot be lower than the intrinsic accuracy of the experimental data themselves. If your training error for the training set is lower than that, then it's not a good sign. It means that your model is actually overfitted. So you don't necessarily want the training set error to be too low. That's a sign that there is something wrong with the model, that it's actually overfitted. So you want your training set error to become equal to the error that you are expecting your model to do. And then the validation set error is going to decrease as the model is learning, and is going to plateau, and it's going to become equal to the training set error, or very close, and it's going to also be equal to the desired performance. So this is what would be the typical signature of a good model. So if you see a learning curve like this, then it means that your model is good. So then it means that it's also not necessary to try to improve the model, because it's just performing as good as it can. So here the typical signature of a good model is that the learning curve of the validation error and the training error becomes comparable to each other. So the validation error become very close to the training error, maybe not exactly the same, but almost the same. That's the sign of a good model in this case. An underfitted model would also show this, but here the difference is that now it's also the same as the desired performance. So it's almost the same as the intrinsic error, the intrinsic variability, the intrinsic inaccuracy of the data themselves. So that's how you can now differentiate from an underfitted model, which would look more like something like this. This is what you would get for an underfitted model. In this case, both the validation set error and the training set error are equal to each other, and they are low. So they are comparable to the error that you anticipate. So this would be for an underfitted model. And the last thing is that you see that the model is learning, and it's plateauing. So the error is not decreasing anymore with the size of the training set. It has reached a plateau. So that's all the signature of a good machine learning model. In this case, your model is as good as it gets. And so it would not help to add more data. It would not help to change the architecture, the degree of complexity of the model. The only thing you could do is to change how fast does the model learn. Like maybe there is something you could change in the model to make it learn faster, but at the end it would still achieve the same final performance. So that would not change the final model. So in this case, this means that that would be a good machine learning model that has been properly optimized, and that is as good as it can be. So again, like the point of this learning curve is that by plotting the learning curve, you understand how the model is learning, as it is exposed to more and more data. By plotting the learning curve, you can clearly figure out if the model is underfitted or not, or overfitted, or if it's just right. And more importantly, based on this, if the model is not doing as well as you would like the model to do, then you can figure out like what is the issue. Is it an issue that you need more features, or is it on the opposite, like that you have too many features? So by plotting the learning curve, you can look at whether the model is overfitted or underfitted, and that's gonna allow you to figure out, do I need more features? Do I need less features? Or maybe is it worth trying to get more data, or is it actually going to be useless to have more data? And so those are all kind of information and potential solution on how to improve your model that becomes easy to figure out when you are plotting the learning curve of your model. So the last advice or general thing to keep in mind when you are working in the field of machine learning is that if your model is not right. Maybe there is a better model that would work better. And for this, it's useful to have some kind of broad knowledge of what are the different methods that are available. So it's impossible for anybody to know all the possible machine learning that are available. There's just too many learning method. There is new method available every day that are being published. So it's just impossible to keep up with all the new things that come out all the time. That being said, having a broad knowledge or being broadly aware of all the different types of methods that are available is going to allow you to have some general ideas of what is available out there, and based on my understanding of the pros and cons of each method, which one should I pick. So if you don't know what's available out there, then it's possible that you might be missing a simple solution on how to make your model more accurate, or you will try a lot of effort, you will put a lot of effort into improving your model, but you will actually kind of reinvent the wheel of, you will place effort into something that has already been addressed by somebody else by making another types of model that you could just reuse directly. So you might waste some time by doing this. And for this, you don't need to be aware of the details of every single method that is out there. You don't need to be expert in everything. And actually, most likely, you cannot be expert in everything. But you just need to have a broad idea of what's available, what are the different types of method, what are the typical strength and the typical weakness of those methods. So it's hard to know this because it comes with experience. It comes with having worked more and more on machine learning, or being curious about the different new techniques that are available, and just try to understand, have a very at least basic idea of the different method. And you don't need to know all the details about each method, but you need to have a broad idea of what's available out there, so that for the problem that you're trying to solve, you can have some intuition about what's the method that you think is going to be the most promising. And whenever you face a new problem, then you will necessarily have to go and learn the detail of the techniques that should be used for this model based on the work that previous people have been doing. Like, it's very unlikely that for two different data sets, it's very unlikely that you will be able to reuse the same model, the same techniques, the same hyperparameters as for the previous datasets. Every dataset is different, so you will always need to use a slightly different techniques or slightly different values for the hyperparameter, etc. So you will need to retune the model, or maybe change from one algorithm to the next every time you move to a new problem, or every time you move to a new dataset. So it's not possible to be expert in everything, and you will need to invest to learn some new things every time you face a new problem. But having a broad knowledge of what's available out there is going to help you make a more informed decision on which model you should be using for a given problem.